Okay, so chapter 3 is the synthesis of sequential circuit. So this is another kind of digital circuit which is very important also. Uh, in chapter 2 we learn how to design the combinational circuit, and both combinational circuit and sequential circuit work together to become a complete digital system. All right. So let's see what we will learn. So we will look at the fundamental of sequential circuit, which is latches and flip-flops. The next one is the bigger sequential circuit as compared to flip-flops and latches. Flip-flop and latches is actually one bit circuit, and register is more than 1 bit circuit. And we will look at another kind of register, we call it shift register, and we will look at the application. One of the application of the register is the counter, and the last one is the memory, how we design a memory. All right, so the memory is one of the sequential circuit. So just like what we have learned, that combinational circuit are the circuit that the value of the output is dependent on the value of the signal that applied to the input, and it will change immediately, all right, after the input change. So that will be the combinational circuit. So for example, the adder or the comparator that we designed just now, when you see, when I change the where is the things, not here already, here, when I change the input here, you see the output here is immediately changed. And again, when I change the input, the output here is immediately changed. So that is what we call a combinational circuit. All right, and comparator is one of the combinational circuit. And for the sequential circuit, now the output of the circuit is not only dependent on the input, but also depend on the what we call a state of the circuit, or the past behavior of the circuit, or in other words is the memory of the circuit. Now for sequential circuit, you have not only the input but also the memory of the circuit. Sometimes we call state. All right. So so here when you see, when the circuit input change value, the new input value either leave the circuit in the same state. All right. So maybe sometimes if you have the new input, sometimes that input cause your circuit, your sequential circuit, to be at the same state. At the same state means that the output will not change, or maybe will cause it to change into another state. All right, where the output may change. All right. So over time, the circuit changes through a sequence of states as a result of changes in the input. All right. So that is why the circuit behave uh, uh, that way. That we call it a sequential circuit. All right. So remember, sequential circuit, the output change depend on input and also the memory of the circuit itself. And for the combinational circuit, the output change whenever the input change. All right. So what make the sequential circuit? So the basic component is latch. Latch, because latch give you a memory. All right, so you can store value in the latch. So this is a very basic latch, or we call it the reset and set latch, or SR latch. So the design or the schematic is just like this, right? Where you have the feedback. All right, one of the input is the feedback from the output, and this is the behavior or the characteristic of the latch. Where when we see that when S and R are 0, so the output Q will not change, right? But when we have 0, 1 here, so QB here is equal to 1, QA is equal to 0, and when 1, 0, so we have 1, 0, and 1, 1, we have 0. So these are the characteristics of SR latch. And when we look at the timing diagram of the output, QA and QB, so this will be the output. So we can see that if 0, 0 here, we can see that the output here is not changed from, right? When we change to 0, 0, output is still the same. But when we change S to 1, so we can see that QA is now go to 1 and so on. So this is the fundamental, the basics. So, and I think you have learned in the previous courses in your undergraduate course already. So we can go fast. And this is, we call the gated SR latch, where we have the clock. All right. So when we have the clock, so we can see that the output at Q is now depend not only for depend on the input, but also depend on the clock. And we can see that when clock equal to 0, the output here is no change regarding not depend on S and R. All right. When clock equal to 0, S and R is don't care. The output will be always no change. And when clock equal to 1, or in this case we call the clock is active, and the output will be just like this. All right. So this is the timing diagram, and this is the symbol. And this is the gated D latch. D latch. This one is SR. This one is D. D latch. D is the represent data. So the characteristic of D latch is like this. When we have no clock, so the output will not change. And when we have clock, when the input is 0, so the output is 0. And when the output is, input is 1, the output will be 1. So it will propagate the input to the output. And D latch is very important in digital system, especially in microprocessor. We use D latch rather than SR, right? And this is the timing diagram of the D latch, and this is the symbol. And come to the next one is the flip-flops. So the latch is actually not very useful in the digital system. All right, sometimes especially in computer. So the one that is very useful is the flip-flop, and of course the D flip-flops. Right. So the different between flip-flop and latch is that flip-flop is age sensitive, and latch is level sensitive. What is age sensitive and level sensitive? Level sensitive is this. All right, means that whenever clock is active, all right, so the output will follow the input. In this case, for example, you see when this here, when clock is active, all right, from here to here, we can see that Q before this not just remain 0 because the clock is not active yet. But here, when active, it will follow the input here, so go to 1 and until the next clock, yeah, all right, and we'll go to 0 because here the input is 0 or D is 0. So, and let's see here, when clock is active, right, here, this one is better example. When clock is active, okay, so now the input or D go to 1, so this will immediately follow. But for flip-flops, flip-flop, the sensitivity is at the edge of the clock only. For example, if we have negative edge like this, all right, so the output or the signal here, Q, will sensitive to the clock edge. So for this one is the negative edge. So for example here, we see we have clock here and D changed already here. For latch, the Q will go to high already, but for the flip-flops, it will go to high when the negative edge of the clock here, all right, so exactly negative edge, so it will go high because D is high here, it will go high, and again it will wait for the next negative edge and look at the input. D is 0 here, so it will go down to 0 and again go up to 1 here because at the negative edge here D equal to 1. All right, so remember flip-flop is sensitive to edge, clock edge, and the latch, it is sensitive to the level of the clock. So whenever clock active, so the output will change. But for flip-flop, it will change only at the clock edge, and the symbol is like this. All right, and what is inside this one is actually you have two latch, two latches. All right, one is master and one is slave, and the connection is like this. So you can look at what is the signal at QM. This is QM and this is the output QS or S, or Q. All right, and we will use this later on. All right, forget about the rest, and this one is the one that we will use in our design. All right, now in Verilog, all right, how to model or create the latch or memory. Right, so the only way is to use the behavioral modeling. All right, so to use behavioral modeling, of course you need to have an always block. All right, for example, if you write like this, okay, always control B, all right, so means that your output will depend on the two signal, which are control and B. So if control A equal to B, but here you see if you have if, we learned in previous chapter, if you have if, you need to specify the else, because if control equal to 1, the output should be this. But what if the control equal to 0? All right, so you need to specify. But if you write this way, so the Verilog compiler will assume that if the signal control here is equal to 0, the output A will remain the previous value. All right, will remain the previous value. So this implies the memory. This implies the memory. All right, it will be something like this. Yeah. If you look at here, okay, if we write the code like this, So you will have the circuits something like this when you synthesize this circuit. So you can have something like this. Oh no, no need to do that. So you have a multiplexer, okay, and if this is control and this is B and this is 1, this is 0, this is A. Right? So you will get this circuit. If you write if control A equal to B. Okay. So normally what we do before this is this. If control equal to 1, A equal to B, else, right, A equal to something else, right? For example, maybe C, right? So that we have something like this. C. Okay. But if we don't have this, so we will have a memory element. Yeah. So when control equal to 0, so the output will be always the previous one, which is A. All right. So this is memory, or will create the memory for you if you write the code like this. So in short, to create a memory, just write the code like this. Then you have the memory element, and this is actually implement the latch. The D latch. D latch is the behavior is like this. Okay. So that is how. Now, how to create a D latch. So this is how. All right, module D latch, D clock. So you have clock, and you have Q. All right, input is D clock, and of course Q you need to declare as output and rack. All right, because why? Because Q is the variable inside the always block, so that you need to declare Q as rack. Always the clock, so this is the sensitivity list. So the output is sensitive to this signal. So if clock, so if clock equal to 1 or clock active, so the output is equal to D. All right, and if clock equal to 0 or not active, the output will be remain the same, right? So this is latch. All right, so this is how to create latch in Verilog. And how to create the D flip-flop in Verilog. So to create D flip-flop, here the declaration part is the same. The difference is that in the always block. All right, so in always block we need to write this. All right, if you have post edge clock or next edge, for you sorry, no one tell me that I not show this again. Sorry for that. I repeat, yeah, I should show this code for you. Okay, so this code is to model the D latch, right? So for our D latch we have D input and clock input, and the output is Q. So input D, clock, and Q, and again Q is inside the always block. So it's why we declare Q as rack, rack. And Q is sensitive to D and clock, so that's why D and clock is should be inside the sensitivity list. So here, if clock equal to 1, so Q should be equal to D, else Q should remain the same. All right, so this is the D latch, behavior of the D latch. And if we want to create a D flip-flop, so what we need to do is this. So the declaration is still the same. All right, always now we need to have this keyword post H. Post H means that our flip-flop is sensitive to positive H clock. So if we want to have negative H flip-flop, yeah, so this is neg H, NEG, all right, so in this case our flip-flop is sensitive to positive H. So now no need to write if clock, just write Q equal to D. Now you have the D flip-flop. All right, that is the difference. So remember, later when you want to create a flip-flop, you need to use post H for positive H triggered flip-flop, and neg H for negative H triggered flip-flop. All right, very easy. All right, now come to the next things that you need to know, which is what we call the blocking and non-blocking assignment. Yeah. What is assignment? Assignment is simply an equal sign that we have learned. So this is assignment. So f equal to x1, this is assignment. X1 and x2. Q equal to D, so this is assignment. But before now, what we learn is only one type of assignment, right? Only the equals symbol. All right, this is called blocking assignment. All right, we have another kind of non-blocking assignment, which is the symbol is like this. We have this, the less than symbol and equal. This is we call non-blocking assignment. What is the difference? All right, the difference is this will impact your design later on, especially when you design the sequential circuit. All right, so before this, here we use blocking assignment here. All right, so remember when we use equal symbol like this, so this is actually blocking assignment. So what is blocking assignment? Blocking assignment is this. When we design or model our sequential circuit, especially the flip-flop, right? And we want to design the circuit like this, all right? Cascaded flip-flops where we have one flip-flop and the output for the first flip-flop is connected to the input of the second flip-flop. And when we design the flip-flop using blocking assignment like this, right? Should be correct, right? It should be correct. Q1, yeah, is equal to D, all right? Or Q1 is assigned to D. D is assigned to Q1. D is assigned to Q1, and Q1 is assigned to Q2. Like this should be correct, right? But what the problem is that when you use blocking assignment in an always block like this, remember that in an always block is the behavioral modeling, and the statement inside the always block is the sequential statement, right? So meaning that the Verilog compiler will use the result of the previous statement to evaluate the second statement. All right, so if you have many statements in your always block, so that statement will be evaluated line by line. First come, first serve means that the first one will be evaluated first, the second one, the third one, and so on. So when we do this, what happens is that we will give, or we will get something like this, right? So when we write Q1 equal to D, and the next one, when we write Q2 equal to Q1, so the Verilog compiler will make the conclusion that because Q1 is equal to D, so it will do the optimization. So if Q1 is equal to D, so Q2 also equal to D. Alright, so it will give you something like this. And this is post age, right? Okay. Instead of this, right? What we want is the cascaded flip-flop like this. Unless you do this, you have to always block, like this. Q1 D, and you have another always block, Q2, then okay. All right, but if you have in the same always block like this, in the same always block like this, what you will get is actually something like this, or only one flip-flop where input is D, output is Q2. All right. Okay, so that is blocking assignment. And what happened when we use blocking assignment in modeling our sequential circuit? All right, so the Verilog offers another kind of assignment. We call it non-blocking assignment. All right, where the symbol is this one. All right, so when we use non-blocking assignment like this, all right, so the Verilog compiler will treat every statement separately, just like we wrote like this. All right, so when we do this, we will get this result when we synthesize our circuit. All right, again, another example here. When we use blocking assignment here, all right, see, when we use the equal sign here, means that we use blocking assignment. So when we use blocking assignment here, we will get this kind of circuit. All right, so because f is equal to x1 and x2, so this should be f. All right, and we have g is equal to f and x3, so g is equal to f here, and x3 or x3 we have g. But if we use non-blocking assignment, we will get the circuit something like this. All right, the f now is the output of the flip-flop, and O of it X3 and we have G, right? That is the difference between the two. So in conclusion, when we use or want to design the sequential circuit, we need to use non-blocking assignment. All right, need to use non-blocking assignment to get the correct circuit. But if we want to model the combinational circuit, we are recommended to use the blocking assignment, just like we did in designing our decoder, in designing our adder or whatever combinational circuit. But when you design the sequential circuit like this, you are strongly recommend to use the non-blocking assignment like this. All right. Okay. So if no question, so we will stop our class here and meet again next week. All right. So thank you. See you next week.